previous lecture, we looked at general features of simple harmonic oscillator, and I told you that a prototype system for this is a spring mass system. So, we keep doing things with this. I did give you one or two examples so that we could relate different things or different systems to the spring mass system. The general equation of motion being mx double dot plus kx equal to 0, and the general solution being xt is equal to c cosine omega 0 t plus d sine of omega 0 t, where omega 0 is the square root of k over m, and c and d are determined by the initial conditions. I could also write the solution can equivalently be written as an amplitude times cosine of omega 0 t plus phi, where the constants a and phi are determined by the initial condition. We also looked at how when I plot xt versus t, it looks like this. That means the motion is back and forth, x goes up to a maximum value, comes down. This maximum value is nothing but the amplitude, and we also saw how to represent this geometrically using a phasor diagram, where we represented the motion as the x component of a vector rotating counterclockwise. Finally, we also saw how the energy of the system is 1/2 k a square, which is really the sum of the kinetic and the potential energy of the system. In this lecture, little complication to the system, and we are going to introduce friction and damping. I am writing these two terms separately because they are going to mean slightly different things. So, let us see what happens when I take the system and let there be a frictional force on the block, called the magnitude of the frictional force F. Obviously, we know from experience, as the block goes back and forth, it is going to lose energy due to this frictional force and finally come to rest. How does that happen? Let us see that. So, if I write the equation of motion, I will have to be careful because the frictional force changes direction according to how the block is moving. Let us first take the case when I stretch the block out and let it go inside. I will now focus on the motion as long as it keeps moving this way and comes to a stop after compressing the spring by this amount. In that case, the equation of motion is going to be mx double dot is equal to the force by the spring minus kx plus a frictional force F. I have written this plus sign because when the block is moving this way, the frictional force is going to be in the positive x direction like this. This equation is valid as long as the block is moving to the left. So, the equation I have is mx double dot plus kx is equal to F, and we have seen this kind of equation in the past. This part is the homogeneous part of the equation and this part is the inhomogeneous part. Therefore, the solution, general solution xt, is going to be the sum of x homogeneous plus x particular due to the inhomogeneous part. X homogeneous I already know is equal to sum c cosine of omega 0 t plus d sine of omega 0 t, and you can verify that x particular in this case is going to be f over k, and therefore, the solution xt is going to be c cosine of omega 0 t plus d sine of omega 0 t plus f over k. This is the general solution, and only after write the general solution that I impose the initial conditions. So, the initial conditions we have this time is, let me first write the solution once again, is equal to c cosine of omega 0 t plus d sine of omega 0 t plus f over k. I stretched the block out, that means I took the block at x equal to 0 to some distance a and released it with no initial velocity. This should be then equal to c plus f over k, and this gives me this equal to d, and therefore, the general solution x t is going to be c, which is a minus f divided by k from this equation, cosine of omega 0 t plus f divided by k. When does the block stop? Let us take x dot of t. This comes out to be a minus f over k times omega 0 sine of omega 0 t with a minus sign. So, when omega 0 t is equal to pi, that is half a cycle, the block comes to a stop, and at that time x t is going to be a minus f over k times cosine pi, which is minus 1, plus f over k. So, after the block started moving left, when it came to a stop, it stopped at x equals minus a plus f over k plus f over k, which is minus a minus 2f over k. So, when the frictional force F is present, by the time it stops for the first time, the block has lost an amplitude of the amount 2f over k. When it goes back, it will again lose this amount. I can later derive the same thing using energy considerations, but right now let us focus on how the motion looks. So, if I were to plot in the first half cycle x t versus t, this curve shows a minus f over k cosine of omega 0 t. What I got to do to this, oh, let me complete this, it comes up to this point, is add it to f over k. So, the solution is going to be, I shift it up by f over k. So, this distance is a, and this distance here is a minus 2f over k. So, you see it has lost that much amplitude by the time it comes here. After it reaches this point here, it starts its journey back towards right again, and let us see what the equation in that case looks like. Equation in that case is going to be mx double dot is equal to minus kx minus f because now the frictional force is going to work towards the left, and therefore, I can write the homogeneous part like this is going to be equal to minus f. I will leave the solution for you to work out with the initial condition that the distance to the left is now a minus 2f over k. You will find that while moving to the right, x t is described as minus a minus 3f over k cosine of omega 0 t minus f over k. Again it comes to a stop after time omega 0 t equals pi. Therefore, x after time such that omega 0 t is equal to 2 pi total after it started the journey right in the beginning is going to be minus a minus 3f over k times cosine pi, that will make it plus minus f over k, which is equal to a minus 4f over k. So during the entire cycle that the particle came this way and went back, it has lost the amplitude of 4f over k. How does the solution look? I already showed you that when I plot xt versus t, it started from a distance a and came up to a minus 2f over k. Then again it loses 2f over k. So when it goes back, it is going to go down, and then its journey starts all over again, going to lose 4f over k again over the entire circle, and therefore the motion dies down like this. How many cycles does it complete? Let us see that. So in each entire cycle, it is losing 4f over k amplitude. So this is the distance it is losing every time. Let us say it completes n cycles. So it would have lost from the initial amplitude a n times 4f over k distance, and it finally comes to a stop. Where does it come to a stop? At a distance f over k, because their friction and spring force, they balance each other, and this gives you n is equal to a minus f over k times k over 4f. That is the number of cycles that the particle would perform before it comes to a stop. As I said earlier, the same thing can be derived using energy methods, and let us see how. When I took this spring mass system, stretched it to a distance a and released it, by the time it stops, it moves a distance up to a1 from its equilibrium position. So after releasing, it would have traveled a distance of a plus a1, and during this time the energy it will lose due to friction is delta E, which is equal to f times a plus a1. Therefore, the initial energy, which was 1/2 k a square, minus the final energy, which is 1/2 k a1 square, should be equal to f a plus a1, and that gives you that a minus a1, you can work out the algebra, is going to be 2f over k. So by the time the mass completed half a cycle, it has lost an amplitude of 2f over k. In the entire cycle, it will lose 4f over k, and then you can work out things as we did earlier. So this is a simple example of how friction affects the motion.